Grounding considerations are paramount when dealing with transformer installations. The transformer neutral, often referred to as X0 or the neutral point, should be grounded at the transformer case. This establishes a reference point for the secondary circuit. Grounding the neutral at the secondary panel is generally not recommended because it can create a closed loop for fault currents, consequently increasing the risk of ground faults. The transformer case itself should be grounded. This provides a crucial path for fault currents, offering protection to personnel from potential electric shock hazards. Similarly, the secondary panel should also be grounded. This again serves the purpose of providing a path for fault currents and protecting individuals from electric shock. The ground connection for the secondary panel should be made from the panel case to either the neutral bus or a dedicated ground bar. Now let's consider a specific configuration, such as a 45 kVA delta-wye transformer. In such a setup, the transformer neutral, X0, should be grounded directly to the transformer case. Furthermore, the transformer case should be grounded to the three-phase bus ground. Finally, ensure that the secondary panel case is grounded to the neutral bus or ground bar within the panel. Regarding earthing, neither the transformer nor the panel should be earth grounded. Earth grounding in this context can introduce dangerous potential differences and paradoxically increase the risk of electric shock. Bonding is another critical aspect. The secondary panel case should be securely bonded to the transformer neutral, X0, at the transformer case. In addition to these guidelines, there are a few more notes to keep in mind. Firstly, all grounding connections must be made using properly sized conductors and appropriate grounding clamps. Secondly, grounding practices should always comply with all relevant local electrical codes and regulations. Thirdly, it is highly recommended to consult with a qualified electrician for any specific grounding requirements that might be unique to your installation. Now let's delve deeper into the reasons behind these grounding recommendations, starting with the grounding of the transformer neutral at the transformer case. The primary purpose of this connection is to establish a stable voltage reference for the secondary winding. Without a solid ground reference, the voltage on the secondary side can fluctuate, leading to instability and potential damage to connected equipment. By grounding the neutral, we ensure that the voltage to ground on each of the secondary phases remains within acceptable limits. Furthermore, grounding the neutral provides a low impedance path for ground fault currents. If a fault occurs between a phase conductor and ground, the fault current will flow back to the source through the grounding conductor. This high current flow will quickly trip the overcurrent protective device, such as a circuit breaker or fuse, isolating the faulted circuit and preventing further damage or injury. As mentioned earlier, grounding the neutral at the secondary panel is generally discouraged. This is because it can create a condition known as a ground loop. A ground loop occurs when there are multiple paths to ground, creating a circulating current. This circulating current can cause unwanted noise and interference in sensitive electronic equipment. In addition, a ground loop can increase the risk of ground faults by providing an alternative path for fault current to flow. Now let's discuss the grounding of the transformer case and the secondary panel. The purpose of grounding these enclosures is to provide a safe path for fault current in the event that a live conductor comes into contact with the metal enclosure. Without the proper ground connection, the enclosure can become energized, posing a serious electric shock hazard to anyone who touches it. By grounding the enclosure, we ensure that any fault current will flow back to the source through the grounding conductor, tripping the overcurrent protective device and energizing the circuit. It's important to note that the grounding conductor must be properly sized to carry the maximum available fault current. The size of the grounding conductor is typically determined by the size of the overcurrent protective device protecting the circuit. Now, let's address the issue of earthing. Earthing refers to connecting the grounding system to the earth, typically through a ground rod or other grounding electrode. While earthing is generally required for service entrances, it is not recommended for transformers or secondary panels in this configuration. The reason for this is that earthing can create a potential difference between the grounded system and the earth. This potential difference can lead to circulating currents and increased risk of electric shock, especially in areas with poor soil conductivity. Finally, let's discuss bonding. Bonding refers to connecting different metal parts of the electrical system together to create a common ground potential. The purpose of bonding is to minimize the potential difference between different metal parts, reducing the risk of electric shock. In the case of a delta-wye transformer, the secondary panel case should be bonded to the transformer neutral X0 at the transformer case. This ensures that the panel case is at the same ground potential as the transformer neutral, minimizing the risk of electric shock. In summary, grounding a delta-wye transformer and its associated secondary panel requires careful consideration of several factors. Firstly, the transformer neutral should be grounded at the transformer case to establish a stable voltage reference and provide a low impedance path for ground fault currents. Secondly, the transformer case and secondary panel should be grounded to provide a safe path for fault current in the event of a short circuit. Thirdly, earthing of the transformer or secondary panel is generally not recommended as it can increase the risk of electric shock. Fourthly, the secondary panel case should be bonded to the transformer neutral to minimize the potential difference between different metal parts of the electrical system. Finally, all grounding connections should be made using properly sized conductors and appropriate grounding clamps, and grounding practices should comply with all relevant local electrical codes and regulations. Consulting with a qualified electrician is always recommended to ensure that the grounding system is properly installed and maintained. It's also important to understand the relevant sections of the National Electrical Code, or NEC, which provides detailed requirements for grounding and bonding electrical systems. For example, NEC Section 250.20 covers general requirements for grounding and bonding, while NEC Section 450.10 covers specific requirements for grounding transformers. Some additional considerations for grounding and bonding include the use of appropriate grounding electrodes, such as ground rods, ground plates, or underground metal water pipes. Selection of the appropriate grounding electrode will depend on the soil conditions and the size of the electrical system. It's also important to ensure that all grounding connections are clean and tight to minimize resistance. Higher resistance connections can impede the flow of fault current and increase the risk of electric shock. Regular inspection and maintenance of the grounding system are also essential to ensure its continued effectiveness. This includes checking the tightness of connections, inspecting grounding conductors for damage or corrosion, and testing the resistance of the grounding electrode. In addition to the technical aspects of grounding and bonding, it's also important to consider the safety implications. Electrical shock can be fatal, so it's crucial to take all necessary precautions to protect yourself and others from electrical hazards. This includes wearing appropriate personal protective equipment, such as insulated gloves and safety glasses, and following safe work practices. If you are not qualified to work on electrical equipment, it's always best to call a qualified electrician. They have the knowledge, skills, and experience to safely install and maintain electrical systems. Remember, proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the recommendations outlined above and consulting with a qualified electrician, you can help to ensure that your electrical system is properly grounded and bonded, protecting yourself and others from electrical hazards. Furthermore, the NEC provides tables for determining conductor sizes for grounding. These tables, such as NEC Table 250.122, specify the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. Understanding and applying these tables is crucial for ensuring that grounding conductors are adequately sized to safely carry fault currents. Proper labeling of grounding and bonding connections is also important. Clear and accurate labeling helps to identify the purpose of each connection and facilitates future maintenance and troubleshooting. Labels should be durable and weather-resistant to withstand the harsh conditions often found in electrical installations. The use of ground fault circuit interrupters, or GFCIs, is another important safety measure. GFCIs are designed to detect small ground faults and quickly interrupt the circuit, preventing electrical shock. GFCIs are typically required in wet locations, such as bathrooms and kitchens, and in areas where electrical equipment is likely to come into contact with water. Surge protection is another important consideration. Surges are transient overvoltage events that can damage sensitive electronic equipment. Surge-protected devices, or SPDs, are designed to divert surge current to ground, protecting connected equipment from damage. SPDs should be installed at the service entrance and at sensitive electronic equipment. Coordination of overcurrent protective devices is also crucial for ensuring proper grounding system operation. Overcurrent protective devices, such as circuit breakers and fuses, should be coordinated to minimize the extent of an outage in the event of a fault. Coordination involves selecting devices with appropriate time current characteristics so that the device closest to the fault trips first, isolating the faulted circuit and preventing unnecessary tripping of upstream devices. Regular electrical safety audits are recommended to identify potential hazards and ensure compliance with applicable codes and regulations. Electrical safety audits should be conducted by qualified professionals who have the knowledge and experience to identify electrical hazards and recommend corrective actions. The importance of documentation cannot be overstated. Maintaining accurate records of all grounding and bonding connections, conductor sizes, and test results is essential for future maintenance and troubleshooting. Documentation should be readily available and updated wherever changes are made to the electrical system. Finally, it's important to stay up to date on the latest electrical codes and standards. The electrical industry is constantly evolving, and new codes and standards are developed to address emerging technologies and safety concerns. Staying informed about these changes is essential for ensuring that your electrical system is safe and compliant. In addition to these specific recommendations, it's also important to foster a culture of electrical safety. This involves training employees on electrical safety procedures, promoting awareness of electrical hazards, and encouraging employees to report any potential problems. A strong safety culture can help to prevent accidents and injuries and ensure the safe and reliable operation of electrical systems. Considering the scenario with a 460 volts delta primary and 120 volts Y secondary, it's crucial to ensure that the neutral point, X0, is properly identified and grounded at the transformer. This provides a stable reference for the 120 volts Y system. The connection from the three-phase bus ground to the transformer case is also vital for safety. This ensures that the transformer case is at ground potential, preventing it from becoming energized in the event of a fault. The secondary panel's ground connection to the neutral bus or ground bar provides a path for fault currents, protecting personnel from electric shock. The bonding of the secondary panel case to the transformer neutral, X0, is essential for minimizing potential differences and reducing the risk of electrical hazard. Remember, all grounding connections should be made with properly sized conductors and appropriate grounding clamps, complying with local electrical codes and regulations. Always consult with a qualified electrician for specific grounding requirements. Following these guidelines ensures a safe and reliable electrical system, protecting people and equipment from potential hazards.